Hello, people of the internet. Today, I'd like to share with you a little bit about differentiation rules. This continues these set of lectures. This is based off of the OpenStax Calculus Volume 1 textbook, and I just wanted to go over some differentiation rules with you folks um, because they're very critical when we move along in calculus. First off, we have our constant rule. So we'll let C be a constant. This is any number, 1, 2, 3, 4, a decimal number, pi, something a constant, right? So we have like 5 or 6 or 7, but it doesn't have to be that. As long as it's a number and not a function, then the derivative of that is going to be 0. So if f of x is equal to x at all x, then the derivative of f of x is 0. So yeah, here we have dx of c is equal to 0, where c is our constant. This one's pretty easy. They say that the derivative is destructive and the integral is constructive. So you're adding more stuff on when you're doing the integral, but because we're just doing derivatives right now, we have this very useful constant rule. Now I will work this example. Pretty easy, doesn't take a lot. I'll cut to live action for that one.
All right, so this is our constant rule example. So as we see here, f of x is always constant at the value of 8. So we know that the ddx of any constant is equal to 0. So f prime here of x is simply equal to 0. That's our answer.
All right, now we're back, moving on. Our second rule is the power rule, right? So we'll let n be a real number. If f of x is equal to x to the n, then the derivative of f of x is equal to n times x to the n minus 1. Or in other words, ddx of x to the n is equal to nx to the n minus 1. Now, it's important that I mention that this is applicable not just for our x to the 3 or our x to the 4 or our 5x to the 2 here, right? Because here this would come down in front, multiply by this 5 if we're taking the derivative. This would be n of equal, so 10x, and then 2 minus 1 is 1, so we don't write that. Here we have 3x to the squared, and here, if we take the derivative of this, then we have 4x to the 3, and that's a pretty straightforward example, but this also works for when our exponent is fractional, and this is another way to write something that might look like this. And it also works for when our exponents are negative. So when we have x to the negative 2, which is another way to write 1 over x squared. So now we'll move on. We'll work some of these examples, and we'll do a couple tricks to show you how this works. And then so I'll move over to live action, and we can do that, and then we'll be back.
All right, so here are our power rule examples. So we'll start off with our first one. We know that if we have the derivative of a power function, so let's say x to the n, then this is going to be equal to n times x to the n minus 1. So for our first one, x to the 10, right? We'll take the derivative of this, and this will be equal to 10x to the 10 minus 1. So this is 10x to the 9. So this is number 1. Number 2, I'll move up here a little bit. This doesn't look like a power function immediately, right? But we know that 1 over x to the 3 can also be written as x to the negative 3. So then we can apply our rule again from up here. So we'll take the derivative of x to the negative 3, and that's going to be equal to negative 3 times x to the negative 3 minus 1. So this is negative 3x to the negative 4, also known as, I'll start again here, negative 3 over x to the 4th. And then our last one, again, a little tricky, little shell game. We know that the square root of x is also x to the 1/2 power. So what we'll do when we take the derivative, this is going to be equal to 1/2 x to the 1/2 minus 1, which is 1/2 x to the negative 1/2, right? So then we rewrite this as 1 over 2 square roots of x, because this will jump to the bottom. So this concludes our power rule examples.
All right, we're back. We're back here on the PowerPoint. Our next rule is the sum rule. The next three rules are going to be very similar, right? So this says that the derivative of the sum of a function f and a function g is the same as the sum of the derivative of f and the derivative of g. So if we have two functions, f of x and f of g, being added together, and we're taking the derivative at the same time, then we can just split them across addition and not multiply, but take the derivative of each finite element. And written in another way here, we have j of x is equal to, if j of x is equal to f of x plus g of x, then the derivative of j of x is going to be equal to the derivative of f of x plus the derivative of g of x. Breaking from form, not another example this time, but we have the difference rule. This tells us a very similar thing to the sum rule, wherein if we have two functions split across subtraction, and we take the derivative of that, then we can end up just taking the derivative of each finite term, and again, written here in this is function notation. And then our last one is our constant multiple rule. So if we're multiplying some function by a number, by constant here, constant k, we can just take that outside and then take the derivative of our function on its own. This is really useful because these constants don't end up confusing anything because they're constants. Constants work pretty well in calculus, and they allow us to do a lot of cool stuff. So here again, if j of x is the same as k times f of x, then the derivative of j of x is equal to k times the derivative of f of x. And so now we have this derivative rule example, and so we're going to use our sum rule, which is similar to our difference rule, and we're also going to use our power rule here and our constant rule. I'll switch over to the live action for that, and then we'll be back.
Here we have our sum, difference, and constant example, right? So if we want to take the derivative of 2x to the 5 plus 7, we know that this is the same as saying dx of 2x to the 5 plus dx of 7. And to extend that, we have a constant here in front of this, so we can move this out. So again, this is 2d over dx x to the 5 plus dx of 7. We know that the derivative of a constant is 0, so we can just write 0 here. And then this will be, the derivative here will be, nx to the n minus 1, so this will be 5x to the 4th times 2. And so then we'll rewrite this as 10x to the 4th. and this will be our f prime of x.
All right, we're back. Moving on, we have the product rule. I think I misspoke earlier. I said we're going to be using the product rule and I meant the power rule, but here now the product rule, the reason for my Freudian slip. So let's say we have f of x and g of x and that they're both differentiable functions. Then the derivative of their product, multiplying them together, is equal to the derivative of the first term times the original second term plus the derivative of the second term times the original first term. So written out here, if j is a function that can be written as the product of two functions, then the derivative of j is the derivative of the first times the second plus the derivative of the second times the first. This one's also really useful because if we can split things into finite elements, we don't have to deal with all of these silly edge cases. So we'll go ahead and work this example in the real world, and I will be back to the PowerPoint in just a second.
All right, here we are with our product rule. Again, we know that the product rule, if we have d dx of f of x times g of x, this is equal to f prime of x g of x plus f of x g prime of x. So here we'll call this first term our f of x, the second term our g of x. So f of x is equal to x squared plus 2, and g of x is equal to 3x cubed minus 5x. And then f prime of x, the derivative here, 2x, right, because this comes down, and then this turns into 0 because it's a constant. And then g prime of x is equal to, this will come down, this is 9x squared minus 5. And then we can write this all out, so we'll have our f prime of x, so 2x times our g of x, so 3x cubed minus 5x. And then we'll add this to our original f of x, which will be x squared plus 2, times g prime of x, which is our 9x squared minus 5. So we'll distribute this in. This will be 6x to the fourth minus 10x squared. We'll have that there, and then we'll have to FOIL this. So this is 9x to the fourth, first, outer, minus 5x squared, inner, plus 18x squared, last, minus 10, right? And then we can combine like terms, so we have like terms here, here, and here. So 18 minus 10 is 8, minus 5 is 3, so this is 3x squared. We have like terms here and here. 6 plus 9 is 15, so we'll have 15x to the fourth. And then our only last term is this minus 10, right? So this should be j prime of x. And we're asked to make sure by finding the product of this original function, so we'll write this again, so x squared plus 2 times 3x cubed minus 5x, and we will FOIL here. So our first terms, this will be 3x to the fifth. Our outer terms, this will be minus 5x cubed. Our inner terms, this will be plus 6x cubed. And then our last terms, minus 10x. We'll combine these like terms. This will be 3x to the fifth plus x to the third minus 10x. And then if we take the derivative of this, we will get 3 times 5 is 15, x to the fourth. This is 3x squared, and this is minus 10. And we see that these and these match up, so we must have done something right.
All right, now that we're back from working that problem, we get to move on to our last rule. This is our quotient rule. This says we let f of x and g of x be differentiable functions, right? Just like the last one. Then the derivative of the quotient of the two functions, so f of x divided by g of x, is equal to the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. The way that I like to remember this is that it's low d high. So this is our denominator. This is our numerator. So low d high minus high d low over low low. This is the way that my calc teacher taught me it. Nice little mnemonic device. We have low d high minus high d low over low low. And you can't see me right now, but I'm doing a little hula girl motion with my hands because that's how the low low, that's how it sounds to me in my head. So now that we have this fun mnemonic, I guess I can write this out in front. ddx of h over L, right? That ends up being equal to that. Let's work an example. So I will not be coming back to the PowerPoint. I will leave you in the real world and we'll work this problem and then we'll be done with our derivative rule examples. Thank you so much for tuning in today. Before I see you in the real world, this is Digital Liam. And remember to like, comment, subscribe, all that good stuff. Click all those buttons. We love it when you click buttons. And have a great day after I'm done working this example in the real world.
All right, here we are with our quotient rule example. And I'll remind you again of our fancy mnemonic device. We have our low d high minus high d low over low low. Like I said earlier, low low. So we'll call this f of x, call this g of x. So we know that f of x is equal to 5x squared. We know that g of x is equal to 4x plus 3. Then f prime of x, here we are doing our power rule, this is 10x. And g of x, we are actually doing our power rule again, but this is to the 1, and then we come to the 0, so then our x turns into 1, so this is just 4. And then our constant rule here, so that's 0. So our g prime is 4. So we'll take our low, so our bottom, 4x plus 3 times the derivative of the top, which is 10x, minus the top, our 5x squared. I'm going to put some more parentheses here just for safekeeping, times the derivative of the bottom, all over our original bottom squared. So 4x plus 3 squared. And then we'll simplify. So this will distribute in. So we'll have 40x squared plus 30x. And then this will we'll multiply these constants, right? So this will be minus 20x squared. All over, we'll FOIL this out. We can, this is the same as 4x plus 3 times 4x plus 3. So our first is our 16x squared. Our inner is 12x. Our outer is 12x, and our last is plus 9. So then we can simplify this even farther and have 20x squared plus 30x all over 16x squared plus 24x plus 9. And this is our k prime of x. Sorry, I cut you off there. There it is again. There is our quotient rule. This will conclude our derivative rules. I know I probably said it earlier, but like, comment, subscribe. Thank you for taking the time to learn calculus today. Calculus is an amazing thing, and you should love it. I hope this bolstered your understanding of calculus. If you have any questions, comments, concerns, there's a comment box for that. I also probably have my email somewhere here, so feel free to contact me. This is Liam Neidig signing out.